A stranger on this Wi-Fi can read every packet you send. So why can't they read your bank password? Hi everyone, my name is Rasa Jamwal, and today we are looking at how the security works behind everything you do online. You type your bank's address and hit enter. Your request does not go to your bank, not directly. It goes to the café's router, then your internet provider, then a backbone carrier you have never heard of. That is 5 strangers minimum, and every one of them touches your request. Plain HTTP hands each one of them a postcard, the address, the form field. So we need two things. Nobody in the middle should be able to read it, and the far end really is the bank. The encryption you already know uses one key. The same key locks and unlocks. Useless here. You would have to send the bank the key first over the wire you do not trust. So we use a different shape, two keys bound together that undo each other. Here is one being made, one command, and out comes a private key. A secret number that never leaves the machine it was born on. From it, you derive the public key, and that one you hand to anybody who asks for it. Lock something with the public key, and only the private key can open it. Because the math only runs one way. Multiplying two enormous primes is instant. Pulling the answer back apart takes longer than the universe has existed. So why not encrypt the whole session that way? Because it is brutally slow. Same laptop, same benchmark. Asymmetric manages about 1700 private keys a second. Symmetric encryption on the same chip moves to 6.5 gigabytes a second. That is not a gap you optimize away. It is a different spot. So TLS uses a slow one exactly once to agree on a key for the fast one. And agreeing on that key is the clever part because they agree without ever sending it. Your browser makes a throwaway key pair. The server makes one too. They swap the public halves in the clear. Anyone watching gets both. Then each side mixes its own private half with the other side's public half, and both land on the same exact number. These are two real runs of that exchange. Different keys, different public keys, same shared secret, and it never crossed the wire. The eavesdropper has both public halves and neither private one, and from there the math is a dead end. That secret gets stretched into a session key, and everything after this point is a fuss. But stop and look at what we just built. You have a perfectly encrypted channel to whoever answered. And nothing in that handshake said who answered. So the attacker on the cafe Wi-Fi does not try to break your encryption. He just answers first. He runs one handshake with you and a second one with a real bank. Two beautiful encrypted tunnels, and he is sitting in the middle reading both. Your padlock is closed. It is closed with him. Encryption without identity is a private conversation with a thief. Which is why the server does not just send a public key. It sends a certificate. This is the real one your browser gets from Chase right now. Read it as a sentence. The public key belongs to www.chase.com. It is valid from December 2025 to January 2027. It belongs to JP Morgan Chase and Company in New York. And at the bottom, the part that matters, signed by DigiCert. Because saying Chase is Chase proves nothing. Anybody can type anything. The certificate is worth something only because somebody else put their name on it. So what does signing actually mean here? Take everything in the certificate, the domain, the public key, the dates, run it through SHA 256 and you get a fingerprint, 32 bytes. Change one character everywhere or anywhere in the document and the fingerprint changes completely. Now DigiCert encrypts that fingerprint with its own private key. That output is a signature. Your browser does the reverse. It decrypts the signature with DigiCert's public key, hashes the document itself, and compares the two. Match. And only DigiCert's private key could have produced that. Nothing else on the earth. But that just moved the problem. Why does your browser trust DigiCert's public key? Because it was already on your laptop before you opened the browser. This is a root store. On this Mac, 158 certificate authorities that Apple has decided to ship. Firefox carries a Mozilla's list, Windows carries Microsoft lists. You never agreed to any one of them, you inherited them with the operating system. And that is where the trust actually stops. Not in maths and not in the network, in a list that came with your machine. Those roots don't sign your certificate directly. They almost never sign anything. A root key is a crown jewel. Compromise it and every certificate under it is worthless. So it lives offline, in a safe, in a room people need two other peoples to enter. It comes out for a key ceremony on camera with witness a handful of times a year. All it does is sign intermediates, and the intermediates do the daily work. So the chain your browser walks is three links. Chase, signed by an intermediate, the intermediate signed by the root, and the root itself signs itself because it is the end of the line. So how does a site get won? You generate the key pair yourself, and the private half never leaves your browser. You send a signing request. Here is my public key, and here is the domain I claim. And then you prove the claim. And that is the only real check that happens. The authority gives you a random token and says, put this at this exact path on that particular domain. You put it there, they fetch it. If it is there, you prove that you control the domain. Let's Encrypt automated that entire loop and made it for free. That is most of why the internet went encrypted, and they expire on purpose. Now the uncomfortable part. Any one of those roots can vouch for any site on the internet. In 2011, a small Dutch authority called DigiNotar was broken into. The attacker issued 531 fake certificates, and one of them was for Google. It was used against around 300,000 people in Iran reading their Gmail. Their browser showed a padlock, and the padlock was genuine. Browsers pulled DigiNotar out of the root store. The company was bankrupt within weeks. So now every certificate gets published to a public log that no one can actually edit. You still can't stop a bad certificate from being made, but you can stop it from being made quietly. So here is the whole thing in the order, in about a tenth of a second. Your browser opens with a hello and its throwaway public key. The server answers with its own plus the certificate chain. Your browser walks that chain up to the root it already trusted, checks the name, checks the date, and checks every signature. Both sides derive the same shared secret and switch to the symmetric encryption. Asymmetric one proved who, then symmetric does the work. And then the padlock appears, and you type your password without thinking about any of it. That's all for today's video on how SSL and TLS work, and I'll see you in the next one.